Thank you. Thanks to the organizers for inviting me. This has been really great here. I've never been to Arkansas, let alone University of Arkansas. It's really beautiful here. So yeah, I'm going to talk about actually kind of a mix of different results, sort of culminating with some newer stuff that I've been working on. And so in particular, I'm going to be talking about the advection diffusion equation, which is, of course, something that a good number of us have been discussing, where the advection is happening with respect to some Markovian velocity field. And, I'm going to talk about chaos associated with these fields, mixing properties, and then what I'm calling normal equivalence, which I'll go into more detail in a little bit. So here's the equation that we all know and love, passive scalar advection diffusion equation. Here I'm just going to work on the torus, but actually some of what I'm saying can totally be done on some sort of compact manifold without boundary, maybe with boundaries. I'm not 100% sure about the boundary case. And of course, the velocity field will be some time-dependent divergence-free velocity field. And I'm going to assume that it's Lipschitz at least, or more regular than that, in fact. So I'm not dealing with anything that's rough. And, we know that if you run this thing long enough in time, the scalar gets very quickly tangled up under the flow. It generates lots of high frequencies, and the high frequencies interact with the diffusion in a pretty complicated way. And you get, you get behavior patterns and sort of things that emerge that are very self-similar, kind of Swiss roll-like patterns as things get mixed, and then they may be pause mixing for a little bit. Particularly if you have flows that are things like fluid flows, like the Navier-Stokes equations, you get lots of vortices that kind of swirl things up, and where they mix, but maybe not actually as fast as you'd like them to be. So it's essentially fast. It's not actually happening. The other thing that's very interesting to study is that for the advection diffusion equation, well, the scalar we know is always going to be decaying because we have diffusion on it. But if you take the scalar and then you kind of turn up the contrast by dividing by the LC norm and study this quantity, you see that very often, depending on the velocity field, it'll settle into some kind of steady state where the thing kind of keeps trying to fold onto itself, but then diffusion kind of stops it. And you get this kind of evolving steady state, which was dubbed by Pierre Humbert as strange eigen. And if I have time, I'll maybe try to talk a little bit about this, but I don't really have any positive results in this direction. So, okay. I'll keep this somewhat short because we've now talked quite a lot about this. But the long time behavior, if I don't put any diffusion on the scalars, of course, strongly depend on the mixing properties that we've seen for the velocity field. So for instance, any sort of scale one blob immediately starts to generate high frequencies because it gets filled with. And so the formation of small scales, it can be measured in a lot of different ways, but sort of typically, at least in this setting, it's convenient to measure it in like an H-1 norm, which, as we mentioned, there's a bunch of reasons for that, but one of them is that, yes, it's like an inverse length scale. It's also convenient just from an analytic standpoint. And so, we'll say that a scalar initial blob like this, if we assume its mean 0, is exponentially mixing if there's some exponential rate such that the H-1 norm decays exponentially fast, at least if I started with initial data that was not, had some regularity to it, something in H1, right? And we know, we've discussed this already, that in the Lipschitz setting, mixing can't really happen faster than exponential. In fact, it's a little bit more general than that. Sort of Sobolev spaces for p bigger than 1. And there's been a lot of work, and I'm not even covering all the things here, but and we discussed this as well quite a bit. But there's been a lot of work studying mixing by given velocity fields or constructing velocity fields that mix in a particular way. So, for instance, I think we've actually mentioned all of these before. Many of these are constructions of velocity fields that mix in a particular way, either in some cases in finite time if they're rough, or exponentially fast, as well as some of the more recent work that was discussed a few times by Tara, Kyle, and Jonathan, which are a little bit more dynamical in nature. And this is something that I'll maybe talk about a little bit more because it's a little bit closer to the methods that I'm going to be discussing, where they use sort of a hyperbolic structure of the dynamics to show that you actually get mixing by fields. And I snuck this one in here too because I didn't really know this reference as well, but Anna mentioned as well. So the whole point of all this is that in general, though, if I just give you a velocity field, it's extremely hard to determine whether it's mixing or not. Okay, even in very simple situations, it's extremely hard to do, and it's even hard to construct them. So the setting I'm going to talk about, though, is, well, okay, if you have a velocity field that has some randomness in it, it makes things a little bit easier. So you don't necessarily have to know everything about the velocity field. You just need to know that it's not doing certain things most of the time. And so the setting I'm going to talk about is that you have a velocity field, which is some random ergodic Markov process. And things become much better. So, I'll mention that the addition of noise, we'll talk about some of the tools in a second, but it allows for tools from the theory of random dynamical systems, ergodic theory, and in particular, the spectral theory for Markov semigroups. And you can use all these things to get a handle on the long time behavior. So in particular, one of the cases, that we've studied is that if U solves the 2D stochastic Navier-Stokes equations on the torus, where the noise is somewhat sufficiently non-degenerate. So it can be, H 1 million or something like that, but it has to have every Fourier mode turned on. Okay. And in such a situation, this is kind of, let's say, the prototypical example. It's perhaps one of the more physical ones. But, you can also consider many other situations. This is not the main example. You could consider anything which is like hyperviscous regularizations in higher dimensions, as long as the equations are well posed and propagate suitable Sobolev regularity, as well as just the Stokes equations or any finite dimensional truncation of your favorite fluid equation. Okay. And in fact, I said it was Markovian, but the velocity fields don't even have to be Markovian. You can, you can consider a much larger class. And in fact, generally, this sort of type of class that we're going to consider allows for a large class of things which are CK differentiable in time, CS. So they don't have to be rough in time or anything like that. They can be regular in time, regular in space. They don't have to be Markovian. And essentially what you have to do is, instead of considering the velocity field, you can augment it with another process that is Markovian. And I'll try to point out sort of where you can make the arguments work in the same. All right. And another example of this, which is the one considered by Alex Michele and Risha, is the Pierre-Humbert flow, which is these alternating sign shear flows that spaceships on. And so all of these kind of fit, I'd say, under the same umbrella of random Markovian, and in particular ergodic, and I'll talk a little bit more about the assumptions there. But yeah, we're considering things like this. So the first result that I'll mention, which is proved by Jacob, Alex, and I in 2019, is if kappa is 0, so we're just looking at mixing, these types of velocities, I'll keep that somewhat loose, they exponentially mix almost sure. So to be more precise, if I have one of these velocity fields that's listed above, think the stochastic Navier-Stokes equations, or actually more generally, if you don't really have a good sense of what the stochastic Navier-Stokes equations are doing, which I don't think very many of us do, you can consider a velocity field that's much simpler like this. So this is take a bunch of shear flows, 4 shear flows on the torus, and that are sort of countervailing, and then just modulate them by independent Ornstein-Uhlenbeck processes. This is good enough to satisfy this thing. And in fact, I think this model would also fit within the techniques that Christian was talking about as well. So there's other proofs, I think, for this kind of setting. So in particular, if this velocity field is one of these ones, then there's some rate such that for all initial data in some Sobolev space, I say S bigger than 100, It's not important, the exact number. Then there's some random constant that depends on the initial data, such that I have exponential mixing. Moreover, sorry, there should not be a kappa there. That's vestigial. Moreover, we have moments on the constants that are bounded by some function, which is a Lyapunov function for the velocity filter. Okay, so for Navier-Stokes, it's something like exponential of the vorticity squared of the answer. But I kind of want to present this in a much more general principle. If you're wondering whether some random velocity field is going to be exponentially mixing, I'd say yes, it is, if the velocity field is sufficiently non-degenerate as a stochastic process. And by that, I mean, that's kind of a vague term. But what I really mean is that it explores a rich enough space of velocity fields exponentially fast. Okay, so if not only it's giving you a whole rich collection of velocity fields that ergodically, but let's say its linearizations are also covering all possible linear phase portraits, then generally you'll get an exponentially mixing velocity field. Okay. So I'm going to give you a, let's say, sketchy sketch of the proof, because it's actually quite long, but here we go. And please stop me if this is all very compact. So if you want me to elaborate on any point, be more than happy to. But generally, the techniques that they're fundamentally Lagrangian. Okay. So in particular, if I look at the velocity field, I'm going to take its stochastic flow, or the flow of diffeomorphisms associated with it, called the Lagrangian flow. And one of the things that we know, and in fact, we've talked about this, Anna's mentioned it a few times, is that mixing, as we defined it in terms of H-1 decay, is equivalent to what I call decay of correlations. So namely, if I take the flow and I compose it with two mean zero functions, which have some regularity, H1 is not important, as long as they have even the tiniest breadth of regularity more than let's say L2, then F composed with the flow integrated on G composed with the flow at time zero decays exponentially fast. Okay. So we say that's exponential correlation decay. And this constant is the same as the mixing constant. Right, so these are equivalent just by duality of H1, H-1. But in general, in the dynamics community, exponential or decay of correlations is studied pretty heavily. Okay, and in particular, it's well known that hyperbolic mechanisms, so things having to do with exponential stretching and compressing locally, give rise to correlation decay in certain settings. Okay, and I should mention that like the stretching and folding property of hyperbolicity is really a local thing, okay? And mixing is a global thing. So just by itself, if I have something that was stretching locally, that would give you something like H1 growth, but it wouldn't necessarily give you H-1 decay. So going from this sort of local mechanism to a global mechanism typically requires some work. But step one, I mean, there are of course really classical discrete time examples of things like the famous cat map or the Baker's map, which have very clear sort of uniform stretching and compressing mechanisms, also sort of Anosov maps. But more generally, right, the way that you can study this is that if you say, let me take my flow, if I linearize it with respect to the initial data, and then look at its asymptotic exponential growth rate, call this Lyapunov exponent. If that exponent is positive, then it has some type of hyperbolicity to it. It may take a while to achieve the exponential stretching, but if you wait long enough, you see it. All right. Although in this setting, just having a positive Lyapunov exponent does not mean that the stretching and compressing that you see is uniform in the space. In fact, generally, it's not. It falls within a category of dynamics known as non-uniform hyperbolicity, which is typically much harder to deal with. So the goal, let's say right now, is to first show this mechanism. Okay, just for the Navier-Stokes, and we did this right by taking by looking at the action of the linear flow, which is belongs to some matrix group, and then looking at its action on projective space or on the sphere. And the reason for this is that like if I take a particle which is advected along flow, so I should have defined this. Xt is just phi, let's say, at some point x. So you have a particle in the flow. You also look at where its linearization is pointing. And it's not how big linearization is. if you keep track of this vectors here, then if I take the velocity field and look at these three things, this is a Markov process. Okay. In particular, it's tracking what the velocity field is doing, it's tracking what a particle is doing, and it's tracking where the linearization or most of the stretching is happening. And in general, VT will align itself really strongly with the direction of most expansion, but it'll also move around all over the place as you let it go. And so one of the things you want to show is that this Markov process is actually non-degenerate in the sense that it converges exponentially fast to a unique state strength measure on this product space. Okay. And to show that, it's more or less a hypoellipticity calculation. All right. I'm kind of writing it very loosely here, but roughly speaking, what you really need to check to do this is if I take the gradient, if I look at the rate of strain of the velocity at a fixed point x, then if I look at the Lie algebra generated by these are all traceless matrices. If I look at the Lie algebra generated by this, where U belongs to all the set of modes, so think really simply, U is the collection of all these possible modes. If that generates all possible traceless matrices as a Lie algebra, then you will have that this thing converges. I mean, there are some other things to be checked, but this is the main thing to be checked, that you have an exponential convergence to unique station. Okay, yeah. What's the theorem?
Yeah, what is it?
I mean, this is essentially Ormonder's theorem with a couple additional pieces. So let's say Ormonder's theorem may be mixed with the Harris theorem. Yeah. But the point being is that, I mean, in order to show Ormonder's theorem is typically enough if you're on bounded evolution, which xt and vt are, but U is unbounded, so you need a Lyapunov function. But we already have that. So Navier-Stokes is known to be exponentially converging to its steady state, or at least any of the fields that we're looking at. All right, and one of the nice things about this measure, in fact, is that the top Lyapunov exponent can just be written explicitly as a linear functional integrated with respect to this measure. So in fact, if I look at this sort of rate of strain of the velocity field at x and two different projective directions, if I integrate with respect to this measure, it gives me the Lyapunov exponent. So what it's telling you is that sort of the statistics that are embedded in this measure will tell you whether lambda 1's positive. And if lambda 1's positive, it's telling you in particular that at most points x and most velocity fields u, the projective directions line up with the unstable directions of the shearing of the strain matrix. Okay. But in fact, lambda being 0, I don't want to get too much into the details about it here because it's perhaps not quite the right audience for it. But there's a well-known rigidity theory due to Furstenberg, which essentially says that. In fact, I should just write this. If I take my measure nu and I disintegrate it, and I condition it on both u and x, and then push it forward under the flow like this, then if lambda equals 0, so having no exponential growth at all implies immediately that you have this condition almost. It means that if you disintegrate this measure, there's an almost surely invariant structure that exists in the dynamics. And in particular, it's a very rigid thing. Okay. And so one of the things you can kind of see already here is that this thing depends on noise, this thing depends on noise, and the nu is not random at all. And so what you can kind of say is, well, if this has to be true almost surely, as long as I can construct a positive probability that this thing does something different than the right-hand side, I can rule it out. So essentially, we can rule it out by using geometric control theory arguments, showing the left-hand side behaves differently from the right-hand side, at least on a small but positive probability set. But the other thing to think about here actually is that if I have it's roughly saying this measure is being preserved by some linear action of a matrix. The real thing to think about here is that if I give you a probability measure and I take I look at the set of all matrices that preserve that probability measure, and this is a probability measure on the sphere, say, I look at the set of all matrices in SLN that preserve that probability measure as a push forward, that set has empty interior. Okay, so generally speaking, this kind of thing is very sparse. It's very non-generic. Okay, so in some ways, this is a genericity thing. Velocity fields generically will have a positively applied. And so now, once you have a positively Lyapunov exponent, I think Christian mentioned this strategy before, is that you can relate correlation decay. So here, I want to look at the probability that I'm not exponentially decaying with some rate q. And just by Chebyshev, I can bound this thing by an integral squared of the expectation of this thing, or the expectation of the square of this thing. I put powers of 2. And if I bring the expectation inside double the variables, this is the expectation of a 2-point motion. So essentially, I've just doubled. I've taken x and I've taken y. They're both evolving in the same velocity field. And so I get the action of this semigroup acting on let's say, tensorized functions. And so what we see is that if I'm trying to show that this thing doesn't happen, okay, I want it to exponentially decay. If I'm trying to show that this thing doesn't happen, then what I'd like to do is use Borel-Cantelli and say that this thing is exponentially rare, right? In a way that, let's say, is summable. And if you know that's true, then you know if you take time long enough, then the opposite thing is true if you allow for some random constant. And so what this roughly tells us is that almost sure correlation decay is related to averaged decay of this 2-point Markov process. I take 2 particles and so I look at this u, x, and t. There's a natural semigroup associated with it acting on functionals. Right. And so this semigroup, I mean, if you like, similar to what Christian had said, is that the generator of this thing can be written exactly as a evolves according to a PDE sort of. This is an infinite dimensional operator, but it has sort of 2 advection operators at x and y, and then it has some generator for the noise or for the velocity field. Okay, and so our goal is to show that this P2 or the evolution associated to this operator decays exponentially fast. And the second you get it decays exponentially fast, you'll know that you mix almost surely. All right. Now, the strategy that we can use here, particularly this level of generality, is there's a tool called the Harris theorem, which allows you to say when Markov semigroups decay exponentially fast. And generally, I think Cecilia probably talked a little bit about this as well. Generally, you need to check 2 conditions. One is the minorization condition, which in our case is not particularly hard to check. The other is a drift condition. And in our case, that's something that's particularly hard to check. And I'll just mention what the drift condition is. It's essentially a Lyapunov function. So what we need to find is that there's some function of u, x, and v, u, x, and y, I'm sorry, that diverges as u goes to infinity and also diverges as x approaches y, that satisfies this condition here. So what this is essentially saying is that asymptotically, as t goes to infinity, this thing starts to forget its initial data. Okay, but moreover, it also tells you that if I look at the level sets of that of this Lyapunov function, that if you leave some level set of this, you actually return to it exponentially fast. So you have really tight control on how frequently you come back to these level sets. So more or less, you can restrict yourself to dynamics only in the level set. And the key strategy that we do here to show this property is that we actually approximate the 2-point motion by another semigroup. And I want to emphasize this thing because this is really at the heart of the proof. Okay. What we do is you take a semigroup. Think of essentially the semigroup now V is the projective of the linearized direction, but you multiply it by the growth of the linearization raised to the negative p power. Now, generally, this factor here is going to decay exponentially fast. But in fact, you can also write this just sort of integrating this explicitly. You can write this as an exponential of exactly the factor that showed up in the representation for the top Lyapunov exponent. So in fact, if you write the generator for this thing, it ends up being like a Schrodinger type. So you're essentially taking the generator for the projective thing and adding this potential with some small factor of P. And one of the things you can show is that this thing in some sense is close to this projective guy. Right? More or less, if you cut things off only near when X is very close to Y, then you can approximate the 2-point motion by its linearized dynamics. Right? And the idea here is that this semigroup can be viewed as a perturbation of just an actual Markov semigroup. So this is not a Markov semigroup. It doesn't send 1 to 1 because it has this factor out front. But if you set P equals 0, you just get the Markov semigroup for the projective dynamic. And this semigroup itself, you can also show converges, as I've kind of mentioned already, it should converge exponentially fast to its unique stationary measure using tools, from Mallevan calculus. Okay, and what that implies, if you sort of turn this geometric ergodicity or the exponential convergence to a stationary measure, it implies that this operator, let's say just evaluated at time 1, has a spectral gap with the top eigenfunction being 1 and the top eigenvalue being 1, which is simple. Right? So there's this picture that, okay, this is just a bounded operator, but there's one spectral value, which is this largest one. It's simple. It sits on the circle, and then there's a gap between it and the rest of them. And we use that quite significantly because we show that if, in fact, if you take P now just a little bit bigger from 0, by essentially Perrin-Frobenius theory, there's some top eigenfunction, which is a positive function, and some top eigenvalue, which is related to the Lyapunov exponent. And in fact, as you send P really small, you can show this thing has to be positive. Where this lambda P, you can actually write explicitly. And if you know a little bit of Perrin-Frobenius theorem, essentially says just take this semigroup and just iterate it or send it forward on the constant 1, and it'll converge to this psi P. But in particular, the rate at which it converges, you can also grab. So this thing's known as the moment Lyapunov function. It's essentially the Lyapunov exponent, but I average before I send P. All right, and the thing about this is that the spectral perturbation theory from this guy will tell me immediately that so this is the top eigenfunction and this is the top eigenvalue, but it's also simple. Because it's simple, we can in fact do a little bit more spectral perturbation theory on it. So now we know that we have this thing which is top eigenvalue and a top eigenfunction. But if we look at this thing, this is basically, it's telling you that psi P is a Lyapunov function for this operator. It's exactly a function with no error terms or anything like this. And so it's kind of cooked up perfectly to play with this guy. And so using this, you can actually show that if I take my Lyapunov function to be something of this form, all right, where this is some smooth cutoff function that says when I get close to the diagonal, I take something that blows up like 1 over x minus y to the p times this eigenfunction plus something that controls the Navier-Stokes piece or the velocity field in general. And if I do that, this gives me the Lyapunov function, and I get exactly this rate for the decay. So putting all that together, assuming any of that made sense, you end up getting the exponential decay of the 2-point motion. And because you have exponential decay of the 2-point motion, you have this almost pure mixing. All right. Now, I should mention what happens when you put diffusion on the problem. So in particular, diffusion, as we know, acts more strongly at high frequencies. Okay, and so if you add diffusion to the problem, it's actually kind of a singular perturbation. And in particular, the mixing kind of feeds into it. So as we've seen before, mixing, if I add a little bit of diffusion onto it, has an enhanced dissipation effect. So there's quite a lot of people who've studied this effect, but generally speaking, I'd say that if I study the decay of the scalar in L2, that if I at least wait long enough in time, I see a rate, let's say C of kappa, which is faster than what you would get naively with the heat equation. It's known, of course, that this rate you can't really get a faster time rate, at least in the Lipschitz setting, than 1 over log kappa. That this is optimal. But if I think as far as I know right now, if I give you an arbitrary mixing flow, it's not clear how to get the optimal rate from just the mixing flow. There are examples now of specific flows where you can construct the optimal rate, but for an arbitrary mixing flow, I think the best work is with Michele, Matthias, and Tarek, and as well as Gautam and 1-1. Well, and so this is the example I was just mentioning. So I think Tarek, Kyle, and Jonathan also proved that you actually do get it with this periodic piecewise constant alternating shears, these sort of wedge flows. All right, but I want to mention that sort of generally speaking, and we saw this with, actually, I should mention Christian's result as well, which is, I think, coming out soon. Generally, if you wanted to get enhanced dissipation, actually more generally follows from something where you get a decay rate that looks like this. Okay, where you have a rate gamma that does not depend on kappa, so you exponentially decay uniformly in kappa, but there's some prefactor that blows up as you send kappa to 0. And essentially, this is what we get when you put kappa. So when you add diffusion to the problem. And so the statement, which I won't linger on too much, but basically we show that if you add diffusion to the problem, that there exists a rate that doesn't depend on kappa, such that for all initial data, there's a random constant which can theoretically, it can depend on kappa, where you get decay like this. Okay, but sorry, but the constant has moments that are independent of kappa. If you average it, you can't take p to infinity, but it has all moments bounded uniformly kappa. And so this actually implies that the enhanced dissipation happens at an optimal log kappa timescale. But I want to mention the thing that makes this challenging in general is that if we just look at the level of the generators or the operators we were studying the spectral properties of, I perturbed it with a high order operator, so this kappa Laplacian. And this is a singular perturbation. It doesn't respect the spectral properties pretty much at all. But the key point of the proof essentially is that if you remember, I mentioned that this sort of twisted Feynman-Katz semigroup was the key spectral estimate you had to get. If you now perturb it with this kappa Laplacian, in general, the perturbation is not continuous for the spectrum, but the dominant eigenvalue and the dominant eigenfunction are continuous with respect to perturbations in kappa. And those are the only ones that matter. And so the second you perturb it like this, you can show that in fact you get this type of an estimate. All right, where because just everything is arbitrarily close to kappa, so I can replace this gamma kappa with the one from the kappa equals 0. So now I want to talk a little bit about decay rates in particular. So as is fairly well known, if you if you look at the advection diffusion equation, there's no known exponential lower bound on the decay rate, L2. So at best, I think you have a double exponential bound that was originally due to Poon. You can prove this essentially with energy type estimates. But I mean, what's roughly happening, or at least the arguments can't rule out, is that because you have exponential growth in frequency, the Laplacian also decays like e to the frequency. You have something that looks like e to the exponential time. So you need to show, for instance, that this thing can't be acting locally in frequency. It can't just be moving a Fourier modes sort of up in frequency. It has to have lots of backscatter. And so as far as I know, this is still the best lower bound. But you know, there are actually explicit examples in discrete time by Gautam that shows that you can get double exponential decay if you pulse diffusion with certain hyperbolic Tor automorphisms. So, you know, it's something that actually can happen in certain circumstances. Whether it happens for advection diffusion on the torus is unclear. But, you know, I actually expect generically it doesn't happen. In fact, this whole thing is related to the presence of a conjectured length scale, which is the backstroke scale. So if I were to look at the H-1 norm of the L2 norm, that this thing roughly sits at an order scale of square root of kappa. So this is more closely related to that strange eigenmode picture that I said. If I took G and I normalized it by L2, then you get this sort of dancing structure where if I look at the typical length scale in there, it'll sit around square root of kappa. All of these are open problems. So showing that this is true and showing that I can get anything better than an exponential lower bound is open. And in fact, sort of a way to rephrase that is it's unclear whether if I look at the asymptotic exponential decay rate of G2, whether it's equal to, I'm sorry, that should say minus infinity. That goes double exponentially fast. But if you do numerics of this, so there's this paper by Charlie and Miles, they basically, I mean, they have very specific flows. They try to construct optimal mixers with some entropy constraint. And they essentially are here looking at the asymptotic exponential growth rate. Let me call that thing gamma kappa. And I'm gonna measure it in different spaces here. So I'm gonna measure it in H1, L2, or H-1. This rate in particular should be it should be negative because we know that the equation is going to be, sorry, this rate gamma is positive. I put the minus sign there. And it's associated with the slope of these lines. Now, what you see here is that if I measure in the H-1 norm, there's a period where the mixing obviously dominates and it has the Laplacian doesn't have anything to act on. But then once you start to generate high frequencies, so you go for this transient period and then all of a sudden you match up with some slope like this. And the L2 norm, for instance, it just sort of remains constant until the high frequencies get generated, and then it goes like this. Same with the H1. It grows for a short period and then it matches. What we see is that the asymptotic rates for all these things are the same. Right? It doesn't really matter what norm you measure. And the other thing that's important to see here is, and this is a way to interpret the uniform and kappa exponential mixing result, is we see that there's this slope right here is the mixing rate for kappa equals 0. Okay, so this is saying how much H-1 wants to decay. But what we see here is that when you add kappa to it, it just increases it slightly. Okay, and so the asymptotic exponential rate for the diffusive problem is bounded by this mixing rate. Okay, and so that tells you that you have uniform and kappa exponential rates just by looking at the picture here. But more generally, we can actually apply tools from the multiplicative ergodic theorem. So in infinite dimensions. So what I want to mention here, and some of this, some of you may not really be familiar with some of this machinery, but I'll try to explain it as simply as I can. We can think of the evolution of the scalar as an infinite dimensional random dynamical system. Okay, and it's sort of this U. I'm describing it as sort of it depends on the entire path, the entire history of U, at least up to time t. So I call it boldface U, the path. And this thing, the semi-group or something like a semi-group is a compact operator. And I'm going to assume that this evolution of the velocity field in the settings that we've been considering, if I move it forward in time, that this is an ergodic evolution. Okay, so there's some measure that it preserves on path space that's ergodic. And under some mild moment assumptions, in fact, if I look at the asymptotic exponential growth rate, this limit always exists. And a priori, I'm going to say it depends on the space X that I'm actually looking at it in. And in general, it also depends on the initial data I started. So this limit exists, and it doesn't depend on the noise or the velocity field. So it doesn't depend on U at all. It's some kind of universal set of numbers that only depends on kappa, X, and G. And this limit holds almost surely. But more generally, what you can say is that for every sort of cutoff, let's call it lambda C some cutoff, let's say spectral cutoff, if you like, then there exists some collection of finite numbers, call it lambda 1 through lambda R, which are all strictly separated from one another and are finite, bigger than this lambda, such that basically there's some filtration of subspaces. And let me just mention, like, the top subspace is just the space X that you're looking at, and then there's one embedded inside it called F2, which is strictly contained inside this one. and has a finite codimension. Okay, so there's only a finite number of things missing from it. And then they all nest inside each other all the way down to this one, which is still an infinite dimensional space. And what you see is that these rates take on these finite set of numbers if I pick my initial data to be in one of the spaces minus the smaller space. Okay, so everything kind of gets dominated by the largest growth. And I should mention, in the way I phrased everything here, all the exponents could actually be equal to minus infinity, because R could actually be equal to 0. And that's definitely a situation you would have if you had double exponential decay. So all your Lyapunov exponents would be equal to minus infinity. But in fact, everything I'm going to say here holds in the case that they all equal minus infinity as well. So the theorem that we prove actually in this case, and it has a much more general version, but I'm not going to present here, is that assume U is this ergodic velocity field. And in fact, it does not have to be random. Okay. In fact, what you can do is you can take Navier-Stokes with a periodic forcing. And then if you restrict everything to the finite dimensional attractor, there's an invariant measure, and then one of them is ergodic. So you immediately have, there's many classes of these things that don't have to be random. But if there's an ergodic velocity field that satisfies this property, where I'm measuring it has finite moment in Sobolev space H gamma for gamma bigger than 1 plus n over 2, then these Lyapunov exponents do not depend on the space that you're measuring the growth in, at least up to minus gamma. Okay, so all of them are the same. And moreover, the spaces that achieve these rates all nest inside of each other. So if I restrict this space to HS2, where S2 is the more restrictive space, then you get a smaller one. All right, so in particular, this means that the H1 rate, the L2 rate, and the H minus 1 rate are all the same, as we sort of saw in Charlie's picture. But moreover, it also says, because we know mixing, so this is the H minus 1 rate, that the lambda 1 is bounded by that uniform and kappa mixing rate away from 0. So the asymptotic exponential growth rates that you get for these advection diffusion cocycles are bounded uniformly away from 0. It's kind of a singular property. Right? And this is not necessarily the case. If you had only, if things were not exponentially mixing, these things could actually converge to 0. It's rate kappa. All right. So in this theorem, it's not just for advection diffusion. In fact, you can apply this to linearized Navier-Stokes, or in fact, magnetic dynamo, so vector advection problems as well. And there's slightly different statement, but it's more or less the same. I'm gonna, in the interest of time, I'm gonna skip this, I think. Oh, okay, I'll mention one thing here. So immediately knowing that that I have the theorem, a corollary of this theorem. Yeah.
One slide. So your assumption is that the expectation of the time interval from 0 to 1.
Yeah. It's ergodic too, so it doesn't. It's okay to just do it in one time step. Yeah. So sort of the idea is more or less this moment condition I can replace in terms of the time 1 evolution of the scalar, if that thing has a bounded logarithmic moments, just the time 1 map of it. Yeah, it's because of the cocycle property in ergodicity. You can just look at time 1. I think actually, because I'm essentially out of time, I will just mention the punchline of this. So the upshot of all of this is that if I want to measure the growth and decay of G of t, the multiplicative ergodic theorem actually allows me to find 2 constants which are finite. So there's a d upper bar and a d lower bar for every epsilon that has an upper bound, which is like lambda 1 plus epsilon, and a lower bound, which is like lambda 1 minus epsilon, with a special factor here that measures how close you are to one of these subspaces. Okay. It's one of these, but let's say it's any Sobolev space where S is between minus gamma and gamma.
But I could put X equal to L2.
Yes.
In which case?
Which case? What do you mean?
Yeah, I was worried that, okay, you have exponential growth, but
No, yeah, they're not, sorry, the lambdas are negative. Yeah, so everything is decay here. And it's this whole lower bound would fail too if you have G in one of these subspaces. Then it'd be the next layout next one you have to measure. Okay, so it's measured in terms of its angle between the two. But moreover, these constants are really valuable, that if you can measure or estimate these constants, they tell you almost explicitly how long it takes for you to reach this exponential rate. So if you wait times that are like epsilon to the -1 log of, let's say, the max of these two constants, then you know that 1 over log GT is epsilon close to this number. So these log of these constants that show up are in fact exactly measuring roughly the length of this transitory period here. And we can estimate these guys, but I think I apologize. I don't really have time to mention that. But yeah, essentially you can estimate these constants and see how they change between Sobolev spaces. At worst, they pick up a log kappa factor, which is still optimal. Okay, that's the proof of it, but I will. Do you have any questions?